ALL represents the most common type of child leukemia, with almost 3,000 new cases diagnosed per year in the USA. In children and young adults with BALL, combination therapy yields high permission rates, with 5-year survival rates currently exceeding 80%. However, relapsed or refractory patients have a significantly lower 5-year survival rate, reaching only 40%. Regarding adult patients over 25 years old, approximately 6,500 patients are diagnosed with BALL each year in the USA. These patients have a considerably poorer outcome compared with children, as their 5-year survival rate stands at approximately 40%. In the relapse or refractory setting, the prognosis of BALL adult patients is very dismal, with a mere 10% alive 5 years after diagnosis. Currently, a wide variety of immunotherapeutic strategies have been developed, harnessing components of both the innate and adaptive immune system to combat cancer cells. Among cell-based therapies, CAR T cells represent the most widely applicable therapy, with already approved commercial products in the field of hematology. The history of CAR T cell production is long, starting in 1992 when T-cell engineering primarily commenced, while 1 year later the first-generation CARs were introduced. Over the next years, further refinement of the first CAR T cell resulted in the advanced breakthrough of the second-generation CARs, which finally led to the approval of the first 2 cell and gene therapy commercial products by the FDA in 2017. Since then, myriads of global clinical trials are on the way, investigating various CAR T cell therapies. During the period from 2017 to 2021, the FDA fully approved 5 CAR cellular products for the treatment of hematological malignancies. Unfortunately, their cost is toxic to the majority of patients and to their insurance funds as well. T cells are genetically modified in order to express a CAR. A synthetic transgene is incorporated into the genome of a replication-defective, self-inactivated lenti or retroviral vector. The vector delivers the CAR transgene to the patient's T cells, where it is integrated into the host cell genome. Upon integration, the CAR gene encodes the chimeric receptor to the host cell surface. The CARs of T lymphocytes against CD19 positive BALL cells consist of an extracellular anti-CD19 targeting domain, which links to cytoplasmic domains via a transmembrane region. Design of CAR T cell and TCR. Schematic illustration of the different regulatory components of CAR T cell and TCR. The following table provides an extensive comparison between the structural and functional determinants of a classic T cell receptor, TCR, and the corresponding components of a chimeric T antigen receptor, CAR T. The first-generation CAR T cells were composed of the intracellular CD3 zeta signaling chain of the TCR, which was infused to a transmembrane and a hinge region. The latter was linked to an extracellular single-chain variable fragment, SCFV, derived from a specific antigen-binding immunoglobulin. This ectodomain recognizes a specific cancerous antigen in an HLA-independent manner, while upon antigen binding, the signal is transduced intercellularly, leading to increased antigen-derived activation of the genetically modified T cells. Second-generation CAR T cells incorporate a co-stimulatory domain, usually the CD28 or 4-1BB molecule, leading to enhanced signaling capability and sustained T cell survival. Third-generation CAR T cells include a second co-stimulatory molecule, while fourth-generation CAR T cells further secrete immune modulatory cytokines. The first step in CAR T cell production is leukapheresis, a process in which white blood cells from the peripheral blood are collected. During leukapheresis, blood is removed from an individual and is passed through a closed system apparatus which separates out the mononuclear cell MNC fraction and returns the remaining blood components back to the circulation. From this MNC pool, the fraction of CD3 positive T cells are isolated and collected in sufficient numbers. Once a patient is eligible for CAR T cell therapy, MNCs are collected through leukapheresis. The next step in the manufacturing process includes T cell enrichment and selection. Afterwards, T cells are activated using anti-CD3/CD28 antibody-coated paramagnetic beads, followed by transduction, primarily with a self-inactivating viral vector containing the anti-CD19 CAR transgene. Subsequently, the modified T cells are expanded ex vivo until there are sufficient cells to meet the final product dose requirements. Following expansion, the transduced T cells are harvested by separating them from the beads, washed, transferred into infusion bags, and cryopreserved. Quality tests are performed before the final product release and shipment to the treatment site. Once the patient is ready to receive CAR T cells, a short course of lymphodepleting chemotherapy regimen is administered, followed by CAR T cell thaw and infusion. After infusion of the autologous product, anti-CD19 CAR T cells circulate through the patient's blood to leukemic sites, including the bone marrow, ready to recognize CD19 positive B leukemic cells and to attack them. CAR T cell kinetics post-infusion has also been a subject of evaluation. Data so far has demonstrated that there is an exponential expansion of CAR T cells during the first 14 days post-infusion, peaking at around day 10, followed by a gradual decline in CAR T cell numbers. By the end of the first 4 weeks, the circulating CAR T cell population in peripheral blood decreased substantially. During this time period, the expanded anti-CD19 CAR T cell population migrates from blood to bone marrow and other lymphoid tissues, exerting its cytotoxic activity against malignant and normal B lymphocytes, both positive for the CD19 surface antigen. Once CAR T cells encounter CD19-containing leukemic B lymphocytes, the anti-CD19 extracellular CAR domain grubs the CD19 antigen present on the blast surface. Upon engagement, The simultaneously activated CAR T cells degranulate and release cytotoxic granules, exocytosis, containing the cytolytic molecules perforin and granzines. These molecules induce the formation of pores on the target cell membrane and apoptotic cell death, respectively. Additionally, multiple stimulated CAR T cells attack the leukemic cells and concomitantly release cytokines such as interferon gamma and TNF-alpha, which contribute to the recruitment and activation of monocytes, macrophages, and dendritic cells, DCs, to the tumor-killing site. These activated myeloid cells act as scavengers, releasing pro-inflammatory mediators such as interleukin-6 and interleukin-1, whose overproduction can lead to the adverse events of cytokine release syndrome, CRS, and neurotoxicity. The timing of cytokine chemokine production is tightly linked to the kinetics of anti-CD19 CAR T cell expansion. Approximately during the first 2 weeks after infusion, 4 major immune mediator programs are activated at 3 distinct time phases. They are characterized by the peak serum values of corresponding specific secreted biomolecules, namely homeostatic, inflammatory, chemotactic, and immune effector biomolecules. CAR T cell therapies are accompanied by several toxicities classified in 5 groups: cytokine release syndrome, neurotoxicity, on-target off-tumor toxicity, allergic reactions, and theoretically risk of insertional oncogenesis. CAR T therapy is associated with CRS, the most frequent toxicity, and potentially deadly if left untreated. It is a systemic inflammatory response caused by the overproduction of cytokines following CAR T cell activation. CRS has occurred with CAR T cells targeting CD19 or BCMA. Briefly, CAR T cells are activated when they engage surrogate antigens and start recruiting myeloid cells through T-cell-derived pro-inflammatory cytokines such as interferon gamma and TNF-alpha. Subsequently, bystander-activated immune cells, monocytes and DCs, secrete interleukin-1 and interleukin-6, which are considered as key cytokines in the CRS pathophysiology. In addition to their ability to cause symptoms of CRS, they can further activate monocytes through INOS, inducible nitric oxide synthase. The ASTCT consensus grading system for CRS, which consists of 4 grades, evaluates 3 patient clinical parameters: fever, hypotension, hypoxia. In grade 1, the patient has only fever. Subsequently, the higher the grade, the higher the toxicity and severity of CRS, which can even be life-threatening, requiring transfer to the intensive care unit. The management of CRS consists of supportive measures, administration of antipyretics, intravenous fluids, and assessment to rule out infection. In severe cases with higher grade CRS, administration of the interleukin-6 inhibitor tocilizumab and sometimes corticosteroids are indispensable. Given the frequency and detrimental effects of CRS, risk factors have been identified and strategies have been developed to prevent it. Neurotoxicity, ICANS, the second most significant toxicity, may occur in the context of CRS or independently. Endothelial dysfunction, increased blood-brain barrier BBB permeability, and brain vascular parasite cytokine-induced stress play a central role in the development of CAR T-cell-associated neurotoxicity. Cerebrospinal fluid has been found to contain high levels of interleukin-2, interleukin-6, GM, CSF, VEGF, as well as CAR T and non-CAR T lymphocytes. These increased cytokine levels may promote the activation of BBB endothelial cells, ECs, and microvascular BBB permeability via EC-secreted ANG2. Permeability is further enhanced by parasite stress, which is induced by the cytokines interferon gamma and TNF-alpha. Clinical symptoms such as confusion, delirium, aphasia, and seizure are typical manifestations of ICANS as a result of brain injury. The following two tables contain information about the ASTCT consensus grading system for child and adult ICANS. Remarkably, patients of all grades require transfer to the intensive care unit. Another common adverse event is long-term B-cell aplasia. CAR T-cells recognize the CD19 antigen on the surface of both malignant and normal B-cells, as CD19 is not a BALL-specific antigen. Along with leukemic cell eradication, normal B-cells are also killed, leading to long-term B aplasia and hypergammaglobulinemia. Regardless of toxicities and the risk of relapse, CAR T-cell therapy remains a promising treatment option for heavily chemo-pre-treated BALL patients. Results from clinical trials using different CAR T-cell products in both pediatric and adult patients have demonstrated high initial complete remission CR rates, reaching even 93%. Despite these promising high CR rates, disease relapses remain a major concern for anti-CD19 CAR T-cell therapy. A significant percentage of all RRB-ALL patients, approximately 30 to 50%, will eventually relapse due to either CAR T-cell exhaustion and incomplete grubbing of the leukemic clone or to antigen escape. The sustained immune pressure attributed to CAR T-cell persistence may cause mutations with modified binding loci on the CD19 surface antigen not recognizable by the CAR structure. Another mechanism of antigen escape is complete antigen loss or even CD19 downregulation, leading to CAR T-cell resistance and finally leukemia evasion. Problems with CAR T therapy do not seem to be with the cell products per se, but with the current therapeutic strategy.